Medtronic technologies impacted more than 72 million people in the last year, equating to 2 people every second. Harnessing the power of technology to take healthcare further, each technology has unique benefits designed to serve patients. The goal of this program is to get closer to the patient and delve into the challenges and impact of each technology in practice. This is the Medtronic MedEd Learning Experience. The Nellcor pulse oximetry monitoring system should not be used as the sole basis for diagnosis or therapy and is intended only as an adjunct in patient assessment. Medtronic's medical education programs are offered to provide attendees education on the FDA-cleared indications and use of our products when applicable. The contents and conclusions of the following program are solely those of the speakers unless otherwise cited. The speakers are responsible for all content and any necessary permissions. The speakers receive funding from Covidien LP, a Medtronic company, for this speaking engagement. For this introduction segment of the series, a discussion on the Nellcor technology. We will discuss engineering Nellcor pulse oximetry, from sensor design to calibration and everything in between. To help provide insight into this topic is Jake Dove, Senior Principal R&D Engineer at Medtronic.
Pulse oximeters can be thought of as a system. There are 3 systems working in unison, a sensor, electronics, and the software algorithm, to be able to report out those values that you're so used to, pulse rate and SpO2. If we walk through that system, the sensor needs to deliver these optical signals, so the 2 wavelengths, so it needs to deliver that light into the patient and then collect that light as well from the patient. It needs to also send those signals to the electronics, where the electronics can measure those optical signals and convert them into something that the software and algorithm can understand. The algorithm will then locate the arterial pulse, because only the arterial pulse is going to convey information related to pulse rate or arterial saturation. Once you have the arterial pulse, then the algorithm can then calculate pulse rate and SpO2. And then display those values via some GUI. To start talking about engineering Nellcor, I wanted to start at the sensor. The sensor attaches to the patient, and these sensors can appear very simple. However, a lot of care has gone into the engineering of these sensors. One example that we can walk through is being able to measure low percent modulation signals. Here we have to have the sensor and the electronics working in unison to achieve high performance. And to show that, we can look at different percent modulation signals, which are shown in the plot below. So here we have a normalized amplitude showing different percent modulations. This is a simple sinusoidal waveform that's being shown. And just for comparison of what a 5% modulated signal would look like compared to a 0.5 compared to a 0.05. As perfusion decreases, so does the percent modulation of our signals. And so at low perfusion, we can expect to have percent modulation signals becoming very low. So at low perfusion, our percent modulated signals decrease. And trying to measure a signal, such as 0.05%, compared to even 0.5 or 5, we can see that noise is going to be very problematic. Noise, which can cause these fluctuations on the signal, needs to be ideally eliminated from those signals so that we can make good measurements of that arterial pulse. Nellcor is actually rated down to 0.03% modulation. Now, 0.5% looks almost like a solid line at this scale. So what does 0.3% modulation look like? If we start to tear apart a Nellcor sensor, what we will find if we cut this sensor cable open, we will find an outer electrical shield. That outer electrical shield, if we unravel it, will expose 2 conductors. Those conductors are attached to the LED. And we also see another inner jacket. If we cut the inner jacket open, we'll see an inner electrical shield that covers 2 additional conductors, and those conductors you can see are attached to a photodiode or photodetector. Now, what's more is that photodiode we can see is covered with something called a Faraday shield. A Faraday shield has been specially designed to allow light to pass through to the photodiode, but block out any electrical noise on these signals. So when that Faraday shield is folded over the detector lines, those conductors, has 100% coverage of shielding all the way from the detector to the board. And it's with this, by shielding these optical signals, we're able to measure all the way down to 0.03% modulation. 0.3% modulation would be similar to trying to detect a blade of grass on top of the Empire State Building. So this, I hope, gives some appreciation when we say that Nellcor can read down to 0.03% modulation. A lot of care has to be taken into the design, especially the electrical design of the sensor and the electronics, to be able to measure these signals accurately. Once our system has been able to pick up that optical signal, the next thing that we need to do is locate that arterial pulse. And so Nellcor takes those optical signals in, and it starts to decrement up that incoming signal. So it needs to find one individual pulse. And the way we do that is we locate these mins and maxes, or the minimums and maximums of that incoming signal. We can define these markers, or these fiducials, to allow us to break up that optical signal into unique pulses. The unique pulses, we need to then decide, is this coming from the patient? Does this reflect their arterial pulse? Or is it noise, some other type of interference? Nellcor has developed a pattern matching neural network that is able to qualify these pulses as coming from a patient or being noise to be ignored. And so this is the first step of processing that the algorithm is going to do, is locate that pulse and qualify that pulse. That neural network, to qualify those pulse, operates on many principles, but two fundamental principles is that the heart is going to pump blood quicker into the arteries, and the arteries will squeeze blood out, and that pulse is going to be consistent. Our heartbeat is going to be consistent, whereas noise is going to happen randomly. By doing this, the pulse qualification neural network will qualify a pulse, and that is when you'll hear that auditory beep, and it sends the pulse then into the SpO2 algorithm. Nellcor, by putting an emphasis on the pulse on that patient, also then is able to achieve excellent pulse rate performance. And we can see this play out in the literature. Here is a study by Corey in 2020 looking at heart rate during neonatal transition. So looking at these neonates, signals from these neonates, and understanding pulse rate performance from 2 pulse oximeters. And so here we can see Nellcor is able to achieve a stable signal in all the patients, that time to stable signal is quick at 15 seconds with a strong correlation to ECG